Welcome to lecture number 14 for ECE 376 Embedded Systems, Data Collection and Calibration. Now the objective here is to set up your PIC so you can collect data over the serial port. What we want to do is collect lots and lots of data over time. That's data collection. And I'd like to do it so it's automatic. I don't want to have to sit there and write down every single number. You're already connected to the computer to download your code. Let's use the computer to collect the data. Second, I'd like to design a circuit which outputs 0 to 5 volts for a sensor, such as a temperature sensor. That's an instrumentation amplifier. And the third thing we'll cover in this lecture is converting the data into something meaningful like temperature. Saying that the temperature is 612 A to D counts doesn't really tell you much. I want to convert it to something like temperature in Celsius, voltage, light reading in lux. That's calibration. So starting out, your PIC is already talking to a computer through the serial port. When you plug in your PIC through the USB port, that creates a USB serial port, and that way you can send data back and forth. That's how you're downloading your programs. With that, I can also send data to the computer and have it record the result of each die roll, record the voltages versus time. The serial port has two lines. It has transmit and receive. There's also a null modem. If you have both the computer and the PIC talking on the same line, then no one's listening and no data goes through. If both sides are listening on the same line, nobody's talking and no data goes through. In order for the serial port to work, you've got to switch the transmit and receive. So the computer talks on one line. That's the same line the computer receives on. And the PIC talks on one line, and that's the same line that the computer receives on. Once you get the connection, and again, you don't really have to do anything for that. Just plug in your USB port to your PIC chip, and you've got the USB port all set up. The second thing is you have to have the syntax, or the formatting for the data. The way the SPI data works is the line idles high. To signify the start of a message, it goes low. The reason for that is if the line is idling high, I have no idea, am I transmitting a bunch of ones, or is the line just idling? The start of message wastes some time, it wastes 1 bit, but it tells the receiver, data's coming. What the receiver does is it synchronizes on the falling edge at the start bit, and then samples in the middle of each subsequent bit, and picks off bit number 1, 2, through 8, or bit number 7. That's what the logic levels are. Then the line idles high again, and you're ready for the next byte. That's asynchronous communication. When you transmit data asynchronously, you have to tell the computer what baud rate it is. Because what it's going to do is it's going to blindly look for the falling edge, that's the start bit, and then just sample blindly at certain spots. If the baud rate is correct, it's sampling in the middle of each bit. If it's incorrect, you're getting gibberish. So you've got to make sure you're transmitting and receiving at the same baud rate. The one we'll be using is 9600. That's a fairly standard baud rate. To do that, you have to jump through these hoops, set these registers SP BRG equal to 255, BRG H1, so on. And that gives you 9600 baud communication. You can communicate at other baud rates too if you want. In terms of software, I need to turn on this code that sets the BRGH, BR16, and so on. This sets up communication to 9600 baud. And then to transmit data, what I do is the hardware actually transmits the data. If I write to a register TXREG, what happens is the hardware then sends out the bits. It sends the start bit, each of the data bits, and then it goes high. The flag that signals that the line is free is TRMT. While it's low, I'm transmitting data. As soon as it goes high, I'm ready to take another byte. So what I do is I wait till the line become free. I'll transmit 8-bit number, wait for it to become free, transmit another 8-bit number. So here I'm just actually kind of idling, waiting about 1 millisecond until the line becomes free. And the serial port, 1310, is carriage return line feed. The other data is in ASCII. So there's an LCD out routine that we've been using. It takes a number and displays it on the LCD. You can do the same thing on the serial port. I'll pass the data, how many digits, and how many decimal places. Just like we did with the LCD routine, pull out the digits by one, and transmit them in ASCII. But instead of sending it to the LCD display, I'll send it to the serial port, TX registers, shifted by 48, and that creates an ASCII character. So let's give an example. Suppose I want to roll a 6-sided die. The following code does that. What I do is I wait for a rising edge. So when I push the button, actually when the button's not pushed, it just waits. As soon as I hold the button down, RB0 goes high. It just counts really fast, mod 6. As soon as I release, that's my die roll. I'll then send that die roll to the display, LCD display. I'll then send that die to the serial out. It's going to be 1 digit, no decimal places, followed by a carriage return line feed. And what that looks like is the following. Here's the super amazing awesomeness graphic user interface that Nate Zimmerman wrote. I'm going to hit the reset button. This is talking to the computer over the serial port. This is the 9600 baud communication that we were talking about. It's the PIC telling the computer that I'm ready to receive data. When I hit program, I'm sending the hex file to the PIC chip as 9600 baud serial data. And once the code is downloaded, when I hit RB1, it's counting really fast. When I release, it sends the number. And notice that was the number 2 in the lower left corner. That's the 2 on the LCD display. Hit it again, I just rolled a 5. And a 6. And another 6. And another 6. And a 4. That's also showing up right here on the LCD or the COM port. I'm receiving data. To record that data, if I clear the buffer, hit the button a bunch of times, and then send that to a clipboard, I can now copy and paste that data somewhere like MATLAB and say dice equals start of matrix, paste, end of matrix. Paste is Control V. I want to see what the numbers are. Those are my die rolls. I can check the frequency. How many times did I get a 1? I rolled a 1 11 times. A lot of 1s there. I got a 2 twice. A 3 3 times. So that's the frequency of each die roll. Just a really convenient way of getting data, and I rolled the die 29 times. So that's one of the uses of the serial port. I can collect data, and I don't have to write it down, let the computer collect the data, then I can import it into MATLAB, Excel, Notepad, whatever you want to do with the data. Second application. On the A to D converter that we covered the other day, I can read voltages. If I read in a voltage as 0 to 5 volts, I can send it to the serial port and then keep track of what the voltages are. For example, if I go over here, I've got the program logger running. This is the voltage. As I turn the A to D input, I go up to 5 volts, back down to 0. If I want to collect data, I'll clear the data, let the data run for a while. We go up to 5, and then back down to 0, and go back and forth a little bit. Once you got the data, I'll copy to the clipboard, go over to MATLAB, if I can find it, there it is. Say data equals start of message, paste, end of message, and then plot the data. So there's the voltage. I started at 0 volts, I turned the pot, went up to 5 volts, turned it down, went up and down. Very quick way to collect data, and in that short time, I collected 113 data points. Again, way easier than writing it down by hand. Some things you can do with that. Suppose I want to measure the voltage across a AA battery and want to watch it discharge over time. Basically, I'm trying to find out how much energy is in a AA battery. One way to do that is connect the AA battery across 10 ohms, have the serial port, or have the PIC measure the voltage on RA0, that'll display, let it run for about 6 hours, and then come back. I'll have the voltages versus time all in a nice file. If I then plot it, here's what it looked like. Here I took data over 6.5 hours, 400 minutes, and the voltage started out at 5 volts. It then dropped down to about 1.3 volts and then tailed off at about 6 hours. So that's one thing you can do. You collect data and see how things behave. Second example, let's look at the voltage across a 2.2 microfarad capacitor. What I'm going to do is there's a 100K resistor that's built into your PIC chip. That's the 100Ks right here, that top one. That's a pull-down resistor to make sure the pins aren't floating. I'm going to use that, charge up a 2.2 microfarad capacitor to 5 volts. At t equals 0, I'll open it up and measure the voltage. When you do that, however, you got to pull the jumpers off on port A. That turns off the light. The lights are pretty, but they're drawing current. That's going to change your reading. Pull the jumper off, and that LED no longer has an effect. I just have 100K and 2.2 microfarads. If I do that, here's what it looks like. I charge it up to 5 volts, release, and it discharges. I can actually take this shape and use that to calculate the value of the capacitance. Third circuit, I could look at a thermistor. Take a thermistor, put it in the voltage divider, and actually that thermistor is going to be in parallel with a 100K resistor. That's built into your PIC board. I can measure the voltage across the thermistor. Once I know the voltage, I can calculate the resistance. Once I know the resistance, I can calculate temperature. So doing that, I can do things like find out when I take a hot cup of water, pour the hot water in, how long does it take to cool off? And again, what you're going to see is an exponential decay. From that, I can calculate the RC time constant. From that, I can calculate the thermal conductivity. If I want to know questions such as, have a hot cup of coffee, does putting a spoon in it make it cool off faster? Does adding a lid reduce the thermal conductivity, make this hold temperature longer? I can start answering questions like that. But to do that, first I have to have a way to collect data. The serial port is a really nice way to do things like collect data on voltage versus time. Another example, suppose I want to know how much energy is my stove. Again, I can run an experiment on that. I'll take a quart of cold tap water, stick it in a pot, turn the temperature on high, and record the temperature versus time. And this is what I get. The same circuit we had before. I measure voltage. From voltage, calculate resistance. Given resistance, calculate temperature. Here's the temperature versus time. And kind of notice the slope is constant. That means the stove is outputting a constant amount of energy. Towards the end, it starts to taper off. This is as it gets hot, the water starts to boil. I'm losing heat through evaporation. And then at this point, that's the boiling point of water. When I get to 100, it's kind of stuck. From the slope right here, I can calculate the energy in the stove. So it turns out my stove is 751 watts when the burner's on high. Now the neat thing about this is the circuit that I'm using is this one. I've got a temperature sensor and a voltage divider. Change that sensor and I can now measure other things. If you go to DigiKey, they have, last count, 19,000 different sensors, and I can measure acceleration, color, capacitance, dust, encoder, flux, float, flow, force, gas, inclination, magnetic fields, light, position, pressure, flow. Change the sensor to any of these, and I can measure something else. That's really the power of data collection. All I need is a new sensor, and I can measure a new item. And it's kind of a blanket offer. The fun thing about electrical engineering is our stuff is affordable. For a couple bucks, I can get you a force, flow, gas, alcohol sensor. In mechanical engineering, it costs you about $1,000 to do anything. In civil engineering, it costs you about $1 million to do anything. In our department, we can actually have fun for affordable amounts. If you want to play with one of these sensors, let us know and we'll get it for you. Up to a limit. If you want a cyanide gas sensor, no, we're not going to get you one. But if you want a flex sensor, so you can sit there and bend your finger and measure how the finger is bending and use that to control your pick processor, yeah, we have those. We'll get them for you. The last topic for today, well, next to last, is instrumentation amplifiers. The A to D reading on the pick works best if the input voltage covers a range of 0 volts to 5 volts. That's when I use the full spread of 0 to 1023. Some sensors don't have a lot of change in voltage, so if I make this the input to the A to D, that voltage is only going to change from say 2 to 2.2 volts. I won't have a lot of resolution. I'll get a better reading if I can take that and spread it out to 0 to 5 volts. That's what the instrumentation amplifier does. This is an amplifier. The gain is R1 over R2. It can either be inverting or non-inverting. Just connect to the VA for non-inverting, VB for inverting. Plus I can add an offset. So this can basically implement any straight line. For an example of what you do with that, suppose I had an RTD. This is another type of temperature sensor. The resistance varies with temperature, not a lot, but it does change a little. Use an RTD to measure temperatures between 0 and 50 degrees Celsius. So I'm going to use the same voltage divider that I had before, just a 1K resistor and R. At 0 degrees C, this is 1000 ohms, and the voltage is 2.5. At 50 degrees C, it's 1200 ohms, and it's 2.7 volts. If I apply this straight to the A to D converter, I'm only using 2.5 to 2.7 volts. I've lost a lot of range. That loses a lot of resolution. What I'd like to do is take that small range and spread it out to 0 to 5 volts. So to do that, what I do is note that the voltage X goes up as the output goes up, so I connect to the plus input. The output should be 0 when Vx is 2.5 volts, so make the offset 2.5. And the gain is the slope. Output changes by 5 volts as the input changes by 0.22 volts. So I want a gain of 22. So make this 22 to 1 ratio. And I made this large because this is actually in parallel with your thermistor. That's going to change the reading slightly. Make that large. It will change it, but not a whole lot. So this circuit will now output 0 volts at 0 Celsius, 5 volts at 50 Celsius. And I can check that in MATLAB. As temperature goes 0 to 50, here's the resistance. From voltage division, that's the voltage at Vx, which is actually VA. The gain that I want is change in output over change in input. I want a gain of 22. The offset is the lower end. That's just special for this case. That's not always true. And the output is gain times A minus B. So if I plot that, sure enough, it's going from 0 volts to 5 volts as temperature goes 0 to 50 C. Now this isn't a straight line. There's a little bit of bend to it. And you can see that. Calibration is trying to come up with a function. What I can measure is voltage, or actually what I can measure is the A to D reading. From what I measure, I want to tell you something. I want to tell you temperature. So from the previous data, up here, I've got voltage, I've got temperature, actually right here, Vy. Vy is the output voltage, T is the temperature. I could also do the A to D reading. I want to find out what is the temperature as a function of A to D reading. So I'm going to pick a basis. My basis is just going to be the A to D reading and 1. It's something that I know. What I want to know is temperature. And the way you do that with least squares is I'm going to say that T is a constant times the A to D reading plus B. Put that in matrix form. So my basis is the A to D reading and 1. To solve for B, it's going to be B transpose B inverse times B transpose times Y. It's going to be this line of code. There's my curve fit. It says the temperature is 0.0488 times the A to D reading minus 0.8. If I plug that in, I get the red line. Notice it's a little bit different. That's my calibration error. If I plot the residual, that's the difference between the actual temperature and my curve fit. That's my basis times my constants. I see this shape. The stair steps are the A to D reading. The A to D is stuck at integer values. And so you're seeing a little bit changes right here. The other shape, the parabola, that's due to the calibration error. that says if I use a linear curve fit, I can't compensate for that parabola. But what I could do is use a more complicated curve fit, such as a parabolic curve fit. If I change the basis to be the a to d squared, a to d and 1, again, something fairly easy to implement in code, I'll just take the a to d reading, square it, times a constant, plus the a to d reading times a constant, plus a constant. That's my estimate of temperature. If I do that, I can get a better curve fit. The procedure is same as before. Pick your basis. A is just the inverse of basis transpose B times B transpose times Y. I get 3 numbers. This is the constant times the square term times the linear term times 1. Now I get a better curve fit. If I look at the residual, the difference between the actual temperature and the curve fit, I get the red line. And now you can see the error is basically 0. The error is really just the quantization noise, the rounding of the a to d converter to the nearest integer. At that point, I really can't do any better, so that's probably the best I'm going to do for a curve fit. So that kind of wraps up this lecture. We've looked at how to get data to the PIC through the serial port, how to get both analog data to the PIC chip, instrumentation amplifier, how to take a reading, amplify it to 0 to 5 volts, and then calibration. Once I've got my A to D reading, 0 to 1023, 0 to 5 volts, how to go back and tell me something that I want to know, like what is temperature, based upon what I do know. That's lecture number 14 for ECE 376, Embedded Systems.